Let's solve some problems. The first problem, list all the subfields of F729, by which I mean a finite field of order 729. So 729 is 3 to the power 6, and 6 has factors 1, 2, 3 and 6. So we have F729, it contains a subfield of order 3 squared, which is 9. It also contains a subfield of order 27, which is 3 cubed, and both those contain a subfield of order 3. The F729 has exactly 4 subfields including itself: F729, F9, F27 and F3. These are the subfields of F729. It is exactly one of each of them. F9 consists of the roots of the polynomial t to the 9 minus t. F27 consists of the roots of the polynomial t to the 27 minus t. And F cubed consists of the roots of the polynomial t cubed minus t. Okay, so that was easy. Let's look at problem 2. How many irreducible polynomials of degree 2 are there in FPT? So I'm asking this question about general FPT. Let's see how the answer depends on P. That's another interesting point. So now one way to calculate the number of irreducible polynomials, maybe let's just make this a little simpler: irreducible monic polynomials. Okay. So one way to find the irreducible polynomials is to start with all polynomials. So there are totally p squared polynomials, monic polynomials of degree 2. Because each monic polynomial is for t squared plus 8t plus b. You have p choices for a and p choices for b. So they're totally p squared monic polynomials of degree 2 in FPT. Okay, irreducible or not. Now from this, let's remove the polynomials which are not reducible. So every reducible polynomial, or non-irreducible if you wish, is, well, it must have 2 linear factors, is of the form t minus alpha into t minus beta, where alpha and beta are in FP. So what we are looking is how many pairs, unordered pairs of possibly repeated elements do I have in FP, and so the number of possibilities is the number of sub-multisets of a set of size p plus 1 of size 2, which is p plus 2 minus 1 choose 2. Another way to see this is, okay, if they have to be distinct, then you get p choose 2 possibilities for alpha and beta, and if they have to be the same, then you get p possibilities for alpha, which is repeated root 2 times. So it's p choose 2 plus p, which is the same as p plus 1 choose 2. So number of irreducible polynomials is p squared minus p plus 1 choose 2, which is just p squared minus p by 2. Okay, let's try a slightly harder one. How many irreducible polynomials of degree 3? Actually here p need not be a prime, we could also take p to be a prime power. All we used is that the cardinality of the field was p. So note that let's call this polynomial phi 2p. It's a polynomial in p, which is itself quite a nice thing. You don't need to calculate it separately for each prime p. Its dependence on p is just polynomial. And phi 1p, let's say, is the number of irreducible polynomials of degree 1. So we have phi 1p, each polynomial from t minus alpha, so this is just p. And phi 3p is, so let phi d p be the number of irreducible polynomials of degree d in FPT. What we get is p cubed is the total number of irreducible polynomials. No, it's the total number of, again, I want to say monic polynomials. So p cubed is the total number of monic polynomials of degree 3. And so this consists of, okay, you can have the irreducible polynomials, which is phi 3p. Then you can have polynomials which have one irreducible factor of degree 2 and one irreducible factor of degree 1. So that's phi 2p times phi 1p. And then you can have polynomials with three irreducible factors of degree 1. Now those factors could be repeated, and so what you get is phi 1p plus 2 choose 3. The number of sub-multisets of a set of size phi 1p of size 3. If you want, you can work through different cases and see if these two are the same and so on. I'll let you figure this part out. And so now we know the values of phi 2 and phi 1, so we can compute phi 3 from that. So what we get is phi 3p is p cubed minus, now phi 2 is p squared minus p by 2 into p plus, and then this is just p plus 2 choose 3. And if you expand it all out, I believe you'll get 1 by 3 p cubed minus p. The next exercise is a fairly straightforward application of Eisenstein's criterion. Prove that t cubed plus 48t minus 24 is irreducible in QT. Now this would be, you just have to find a prime p with which we can apply Eisenstein's criterion. So you look at the factors of 24. 24 has two prime factors, 2 and 3, but it's divisible by 4, so you can't use p equals 2. However, you can use p equals 3. It's divisible by 3, but it's not divisible by 9. So just take p equals 3 and apply Eisenstein's criterion. Okay, and let's look at problem 5, which is another irreducibility problem. Is x to the 4 x to the 4 no yeah x to the 4 plus 4 irreducible in QX? Now, it would be tempting to say that Eisenstein's criterion does not apply to this polynomial because the only p I can take is 2, but p squared divides 4. So the only so Eisenstein's criterion does not apply to this polynomial, and therefore it is not irreducible. But that's not correct. Eisenstein's criterion only gives a sufficient condition for a polynomial to be irreducible. If Eisenstein's criterion does not hold, that does not automatically mean that the polynomial is not irreducible. So we need to work a little further and try to examine this. Now note that x to the power 4 plus 4 does not have any linear factors because x to the power 4 plus 4 does not have any rational roots. So we would be looking for a factorization into two quadratic factors. So let's try, and we should have x squared plus x to the power 4 plus 4 should be a product of two quadratic factors, and we know that we can choose them to be integer polynomials by Gauss's lemma. So they must be of the form x squared plus so you can have ax plus 2 into x squared plus bx plus 2, or you can have x squared plus ax plus 4 into x squared plus bx plus 1. But let's just try this and see if we can find a and b. But if you expand this out, so we don't know for sure that we have a factorization like this, let's just try it. And so if you expand this out, you get x to the power 4 plus a plus b x cubed plus 4 2 here and 2 here, so 4 if we want x squared, 4 plus ab x squared plus 2 into a plus b x plus 4. So that's the thing. So what we must have is that a plus b is equal to 0 and 4 plus ab is equal to 0. And so that this means that b is equal to minus a, which means that 4 minus a squared equals 0, which implies that a equals 2, b equals minus 2. So we have a factorization. 4 plus 4 is x squared minus 2x plus 2 into x squared plus 2x plus 2. Well, if you were a little observant, you may have noticed that this is x to the power 4. So this is an a plus b into a minus b form. So it's x squared plus 2 minus 2x into x squared plus 2 plus 2x. So this is can also be solved in that way by guesswork. So x to the power 4 plus 4 is not irreducible in qx. Eisenstein's criterion does not apply, but that's not enough. You actually need to show that it is reducible.